Okay, finishing classwork 7.3 from where we left off. I want you to make a table for all these values that we know of tangent x, and cotangent is always the reciprocal. So that's going to allow us to get through this a little bit faster. Now, at angle 0, we looked at this yesterday. At angle 0, if I look at the y divided by the x, y is equal to 0 where x is 1, so I end up getting 0 for my tangent. And the reciprocal of 0 is actually infinity, undefined. Then I'm moving on to pi over 6. So when I'm at angle pi over 6 here, the y-coordinate is 1/2. The x-coordinate is √3 over 2. And that means that I'm getting a value of tangent that is 1 divided by √3. The reciprocal of that is √3, and that's what the cotangent is at pi over 6. At pi over 4, do you remember that this is where the y and the x coordinates are equal? The tangent value is 1 at pi over 4. And so cotangent, it's also a value of 1. When I move over to pi over 3, at angle pi over 3, my x and y are actually swapped from what it was at pi over 6. The y-coordinate of this point is √3 over 2. The x-coordinate is 1 over 2. So that means that the tangent's value at pi over 3 is √3. When I reciprocate that for cotangent, I get 1 divided by √3. Then for pi over 2, pi over 2 is where if I draw a line through the origin, it's got an undefined slope. And also if I look at the y-coordinate, which is 1, divided by the x-coordinate, which is 0, I'm getting undefined. However, for cotangent, cotangent looks at the x divided by the y, and I'm getting 0. Then I'm going to go through the rest of these a little bit faster. So 2 pi over 3, the tangent value is showing actually a negative x-coordinate with a y-coordinate of positive √3 over 2. So I'm getting negative √3. The reciprocal is negative 1 over √3. When I go to 3 pi over 4, halfway through my next quadrant, my slope is negative 1, and the reciprocal of negative 1 is negative 1. And then when I hit 5 pi over 6, that's when the slope is the same as it was here, but negative instead of positive. I'm getting negative 1 over √3 for the tangent. The cotangent is the reciprocal of that. Then when I get back over here to pi, that's where I go back to the slope of that line is 0, or the y divided by x is a 0 over 1. But the cotangent is undefined there. Because with cotangent, I'm looking at the x, oh, sorry, it was a negative 1. The x-coordinate is negative 1 divided by the y-coordinate for cotangent. I'm getting undefined for cotangent. And then I'm going a little bit further down the line here. I want to quickly go over to pi over 2. Or wait. Did I already? I already did pi over 2, so why do I have pi over 2 again? I think I meant that to be 3 pi over 2, but on the sheet that I gave you guys, does it say 3 pi over 2? It doesn't? Okay, I need to remember to fix that. But what I'm going to do is just go over to the answers on that. Yeah, I fixed it on the answer key. And I want to make sure that you're aware that undefined means infinity in these situations. And also, just to point out, the square root of 3 is approximately 1.7, and 1 divided by the square root of 3 is approximately 0.57. And what we're going to do is we're going to plot these points on the graph, on the graphs of tangent and cotangent. So, coming back over to here, and plotting some of these points. My tangent value at 0 was 0. And right now I'm graphing the tangent graph. My tangent value at pi over 4 is, I'm actually going to skip a little bit here. And I'm going to plot that at pi over 4, my tangent value is 1. At pi over 2, it is undefined. And the undefined slope is actually because it's infinity. And I want to show you something real quick. I have told you that tangent is sine over cosine before? Okay. If you look at the fact that tangent is sine over cosine, and then you remember with rational functions. With rational functions, when the denominator is 0, you get a vertical asymptote. Cosine is 0 at pi over 2 and 3 pi over 2. Those are the places where my tangent is undefined, but it's undefined because it has a vertical asymptote. So I'm going to draw a vertical asymptote at pi over 2. And at 3 pi over 2. And keep plotting the points, and then I'm going to come back to the issue of sine over cosine. Plotting more of these points. At 3 pi over 4, my tangent value is -1, and at pi, my tangent value is 0. I'm going to plot those 2 points. So 3 pi over 4 is -1, pi is 0. Then 5 pi over 4, you would have gotten -1 there. Wait, not -1, +1. Just realized that. And so you can begin to see a little bit of a pattern here. Now in the future, you're not going to want to sit here and go through all those numbers and plot these points. I have some of the other angles there just to fill in a few gaps to help us a little bit. 1 divided by √3 and √3 were the numbers 0.57 and 1.7. So if I add those into the mix, then I've got points approximately here, and approximately here. Sometimes this program is frustrating. Okay. If I add some of those points in this next section, then what I'm going to find is that I have some additional points, and I'm going to throw those in there. And I'm trying to be reasonably accurate, but I'm not going to be perfect on this. It's so-so. This should actually be up a little bit higher, I think. But if you sat down and like just plotted all those points, you would see this pattern. If I look in between these two asymptotes, so I'm looking between pi over 2 and 3 pi over 2, do you see that it looks like it's just heading up? And it actually is doing that. When I am working with graphing tangent in between a pair of asymptotes, all it does is just start at negative infinity and then increase and then go up to positive infinity. It looks a little bit like x cubed, but x cubed has a boxier graph to it. X cubed flattens in the middle, but tangent just kind of continues up. It's a little bit of a bent line. Now, you're going to very likely in the future remember about what tangent looks like, but not remember exactly where to place it or the fact that it heads up versus heading down. So what I'm going to recommend for your future remembering is when you need to graph tangent, first remember that it's sine divided by cosine. And then remember with your rational functions that you get vertical asymptotes when the denominator is 0. You get x-intercepts when the numerator is equal to 0. Sine is equal to 0 at 0, pi, 2 pi, 3 pi, 4 pi, negative pi. And then vertical asymptotes are where cosine is 0. Cosine is 0 at all of the pi over 2's. So 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative pi over 2, and then it goes off grid. Tangent is going to continue to have this shape to it. And by working out some of these numbers in this chart, I'm hoping that you'll see that this pattern just is the same as you go along. So now I'm doing a kind of a quick draw, but I want to do a little bit better than a quick draw. There we go. So tangent is always moving from left to right upward. And you want to remember where tangent has its vertical asymptotes and where it crosses the x-axis. But I want to remind you and say it again. If you remember that tangent is sine over cosine, and you can remember from rational functions that the denominator being equal to 0, vertical asymptotes, numerator being equal to 0, x-intercepts. So that's the graph of tangent. For the graph of cotangent, if tangent is sine divided by cosine, then cotangent is cosine divided by sine. And I'm going to fill in some of the missing blanks, but I'm going to start with anywhere that sine x is equal to 0, cotangent has vertical asymptotes. Sine is equal to 0 at 0, pi, 2 pi, 3 pi, 4 pi, and if I go backward, negative pi. The other thing is when the numerator is equal to 0, I have my x-intercepts. Cosine is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative pi over 2. But cosine doesn't go the same cotangent does not go the same direction as tangent. If I go through and I plot these cotangent points that I have down here, I'm going to see that I am getting, and I'm just going to plot those points. I'm going to approxiplot the things that are kind of not on this grid, and actually that should be higher. And so just kind of throwing in those approximation numbers, because those are the numbers for root 3 and 1 over root 3 for the tiny dots. By just looking at those, do you see that cotangent heads downward? That's the difference between tangent and cotangent graphs are whether it heads upward or heads downward. And also it's about the positioning of the asymptotes and the zeros. And I'm going to plot the pi over 4 numbers, all the x coordinates that are multiples of pi over 4. Those are 1 and negative 1, and then draw the graph from there. In the future, you're not going to want to come up with a table like we did at the beginning. I needed to have you look at the table to fill in the blanks of some of these in-between points so that you could feel comfortable with the fact that this is what it draws without going too deep into the numbers. And again, the main thing is, if you write them in terms of sine and cosine, then you just need to remember when the denominator is 0, vertical asymptote, when the numerator is 0, x-intercept. And then it's a matter of remembering which one heads up and which one heads down. And you can always point plot if you need to. One trick that I want to let you know about. Your trig functions are positive when you're in quadrant 1. Quadrant 1 is when you are working between 0 and pi over 2. You have only positive values for your trig functions. So if you can get the location of the zeros and the location of the vertical asymptotes, and you can't remember with tangent and cotangent whether it heads up or down, what you can do is look at 0 to pi over 2 must be positive. 0 to pi over 2 must be positive. And if you can get those regions shaded, and then just remember that the graph either heads up or it heads down, you've got the graphs. I'm hoping you'll see that you don't have to do too much work. So what I've got down here is what's going to help you remember these graphs. So the graph of tangent x. Actually, let me just go over here so I can just point it out. What I've got here is for number 6, when sine x is equal to 0, tangent is sine x over cosine x. Cotangent is cosine x over sine x. So the angles where sine of x is equal to 0 give you x-intercepts with a tangent graph and vertical asymptotes with a cotangent graph. And the angles when sine is equal to 0 are 0, pi, actually I'll put plus or minus pi, plus or minus 2 pi, plus or minus 3 pi. Then when cosine is equal to 0, tangent has cosine for its denominator. That's going to create vertical asymptotes when cosine is equal to 0. Cosine is the numerator for cotangent, so that's going to provide x-intercepts. Cosine is equal to 0 at angles plus or minus pi over 4, or no, what am I thinking? Pi over 2. I'm on the wrong angle. Plus or minus 3 pi over 2, plus or minus 5 pi over 2, and I could keep going, plus or minus 7 pi over 2. So all the odd pi over 2s. Now, if you look back at the graphs, I want you to take a good look at the range and the domain. I want you to see with the range that every single y value is accounted for from negative infinity to positive infinity. We have a range of all real numbers. The domain happens to be everything except the vertical asymptotes. So the domain of tangent is all real numbers except for the pi over 2s. For cotangent, it's all the multiples of pi. And actually, I don't need to have this written here. That could just be pi times n. So basically, all the over 2s or all the just plain pi's are kept out with where those vertical asymptotes are. And also, did you notice that a cycle is done in only a pi amount? So the period of tangent and cotangent is pi. For all of the other 4 trig functions, the periods are 2 pi. Now, the examples for the classwork are going to be practicing sketching these graphs. And let me see, and then also finding equations. So here we go. I'm going to show you how I personally would go about graphing these functions, and then you can decide how you want to manage it. Secant is 1 over cosine. And if you remember from yesterday, I had you dash graph cosine, and then from there draw the secant graph. What you can do, if you want, is you can graph the actual cosine of 2x and then do the same thing. So what I'm going to do is start off with cosine x. Cosine x is at its highest point when I'm at angle 0. At pi over 2, it's midline, pi, lowest point, 3 pi over 2, midline, 2 pi, highest point. If you want, you can go ahead and deal with the multiplication by 2 directly on your cosine graph. So what I'm going to do is first finish with putting more of these dots. And, whoops, went too low there. If I were graphing the cosine of 2x, I see that x is multiplying, so I need to actually divide my x's by 2. And that means that 0 divided by 2 will still be 0. And then each of these x coordinates is going to be cut in half. Let's see, 3 pi over 2 cut in half takes me all the way over to here. 2 pi cut in half takes me all the way over to pi. And this problem asks you for 2 cycles. So I'm going to go ahead and draw 2 cycles worth. Right now I have 1 cycle of my cosine function. I'm going to erase those arrows and the original points. To get a second cycle, I could just watch this pattern and repeat it. That's going to show me where my 2 cycles of cosine are for cosine 2x. I'm going to dash graph it. And now secant has vertical asymptotes where its same graph as cosine has vertical asymptote, is equal to 0. So I'm going to draw vertical asymptotes where I have x-intercepts. And I'm going to go ahead and bring this over here because these graphs are a lot nicer between asymptotes than to cut it off. And now I'm going to officially graph the secant. Shares that highest point, shares that lowest point, and it's just going to keep going back and forth. Now, what you could also do is you could have just stuck with the graph of cosine x, graphed secant of x, but then taken that graph of secant x and divide all of its x's by 2 and squish it in. However you get to that final graph is how you get there. I'm going to erase this gray part to show you that, oh, I didn't mean to do that. Okay, maybe I shouldn't do that. But basically just make sure you're clear that the cosine graph isn't the graph that we are actually drawing. It was used to help us graph the secant graph. Cotangent. We just recently graphed cotangent. So in the future, you're going to not remember exactly what it looks like, but you're going to remember that cotangent is cosine divided by sine. And that we are going to have vertical asymptotes where sine is equal to 0, which means 0, pi, 2 pi, and so on. So I'm going to draw vertical asymptotes. And if you want to shift this while you are doing this graph, you can. I'm just going to show this in a slower step-by-step manner. Then the other thing to remember with cotangent is the function who is its numerator tells me where my x-intercepts are at. My x-intercepts are where cosine is equal to 0, which is negative pi over 2, pi over 2, 3 pi over 2, all the over 2's. So I'm going to plot those points. The other thing to remember about cotangent is whether it heads upward or downward. And if you can't remember, do remember that one thing is true about all trig functions. When you graph them between 0 and pi over 2, they only exist where y is positive. And then if you bring together how you understand vertical asymptotes to work and recall basically that cotangent does this, then all you're going to do is repeat that process. Now, plus pi over 4 means everything is going to move left pi over 4. So what I'm going to do is I'm going to start moving everything left pi over 4. And I'm going to first erase a bunch of stuff, but leave a little bit. What I really want to remember is where are my x-intercepts, where are my vertical asymptotes. So what I'm trying to do is leave showing where the asymptotes are at and showing where those zeros are at. And I'm going to move all of them pi over 4 to the left. So this is going to disappear off grid. This point will move left a pi over 4 amount. My vertical asymptote is moving a pi over 4 to the left. X-intercept left pi over 4. Vertical asymptote left pi over 4. However, you were only asked to graph 2 cycles, So this is more than enough. And what I'm going to do is, actually, I'm just going to draw more just because I can. Know that you're only expected to draw 2 cycles. So now I know that for my final graph, I've got my vertical asymptotes. And then the graph for cotangent heads downward. Again, you only have to draw 2 cycles. I've just drawn 3 cycles, 3.5 cycles actually. So there we go. The other thing you're going to be asked to do is figure out what equation each of these are. Make sure you pay attention to the equation given. You only need to figure out what is that number b, and you're told it's a tangent graph. Normally, tangent has its asymptotes, its vertical asymptotes. Normally, they show up at, do you remember where? Where are tangent's asymptotes normally? At the pi over 2's. So these are all the places where tangent normally has vertical asymptotes. Tangent normally goes through the origin. Can you see that the asymptote that would normally be located at pi over 2 has been stretched out to 3 pi over 2? And you can figure out your b in a way different from what I'm doing. What I'm looking at is, what do I need to multiply to pi over 2 to get to my 3 pi over 2? Three. When it comes to the inside multiplication division, if you have to multiply by a number on your graph, you're actually dividing by that number in your equation. If you have to divide the original position numbers by a number, you're going to multiply the equation. So you're just bringing an opposite operation. You can see on the graph that you have to multiply pi over 2 by 3 to see where it's stretched to. So that means I'm going to divide my x by 3. And there's your equation. And then I have one more example. This one is looking at the graph of cosecant, but this is also letting you know that the only thing you need to account for is what is needing to multiply outside the function and how far does it move up vertically. So let me tell you this. If this was a sine or cosine graph, that sine or cosine graph would share these points. So can you connect those high and low points? Now, I didn't draw my sine function perfectly, but if you look at it, I'll try to tidy it up. You notice that this, and by the way, sine is cosecant's reciprocal. So we know we're looking for a sine graph. The lowest point of this sine graph is 1. The highest y value is 5. What number is halfway between 1 and 5? 3. So that actually tells me that the midline of my sine graph is 3. And to get that midline, I have to move the function up 3 units. And that is exactly what I'm doing to the cosecant graph. For this sine graph here, now that I know a little bit more, I'm going to bring in some extra points to make it a little bit more accurate. What is the amplitude of this trig function? For the sine graph, what is the amplitude? That means what is the distance? Now, everything that is affected vertically is by the same operation. If I have to stretch my sine graph by 2 to create that amplitude, my cosecant graph also has to multiply by 2. But there's one extra little catch. Do you see that this is a sine graph that is upside down? Because if I look at where I'm located at time 0 and then where I'm located at time pi over 2, my sine graph is heading down before it heads up. So that means it's -2.